Okay, we've got the two reference dipoles set 2 meters apart, 1.5 meters above ground level, and we've calibrated the nano VNA to establish a 0 dB situation between the path between these two dipoles. So this is the two dipoles in horizontal polarization. Just for reference, because one of the things we are looking at here is polarization, is I'm going to rotate one of the dipoles 90 degrees, so it will be in the vertical, and the sensing dipole will be in the horizontal. So we should see a fairly dramatic loss once we do that. Just let things settle down. And that has introduced a path loss of greater than 21 dB. So we're going to have to just change the scale on this, make each increment 4. Bouncing around a little bit, but I'm going to call it somewhere in the middle here as being minus 28 dB, and that's theoretically what you should expect to see with cross-polarization. The reference antenna has been swapped out for the antenna under test, which is a Skew Planar Plane Antenna for 435 megahertz. So we're going to do a few tests. The obvious comparison immediately is the gain compared to a dipole. So with the sensing antenna, which is a 435 meg dipole, in the horizontal plane or horizontal polarization, and the antenna under test, the Skew Planar Plane, at 0 angle, pointing straight up I guess, or sideways. So it's recorded as 0 degree angle. In the horizontal plane we are recording minus, we'll call it minus 8 dB. So we're now going to tip the sensing antenna into the vertical plane, vertical polarization, and record those results. To allow things to settle down. Okay, with the antenna under test in the 0 angle and the sensing antenna in the vertical position, we are recording minus 7.4 dB. So straight up, that's very interesting. We're cross-polarized. When we did that with the sensing antenna and the reference antenna, cross-polarization gave us a loss of 28 dB. Now we've lost almost half a dB with the cross-polarization in this plane. So now I'm going to tilt the antenna under test, the Skew Planar Plane, 5 degrees towards the sensing antenna. Okay, with the sensing antenna still in the vertical plane and the antenna under test now tilted at 5 degrees, we are recording minus, we'll call it minus 6.7 dB. We're now going to tilt the sensing antenna into the horizontal plane. Just let things settle down. Okay, with the sensing antenna now in the horizontal plane and the antenna under test tilted at 5 degrees, we are recording minus 8.0 dB. Okay, now I'm going to tilt the antenna under test another 5 degrees, so a total of 10 degrees tilt angle. Okay, with the sensing antenna in the horizontal plane and the antenna under test now tilted at 10 degrees, we are recording minus 6.8 dB. We're now going to move the sensing antenna into the vertical plane. Okay, with the sensing antenna now in the vertical plane, the antenna under test at 10 degrees, we are recording minus 5, call it 5.7, minus 5.7 dB. Okay, I'm going to now tilt the antenna under test another 5 degrees, so 15 degrees. Okay, with the sensing antenna in the vertical plane and the antenna under test at a tilt of 15 degrees, we are now recording minus we'll call it minus 5. Okay, we're going to move the sensing antenna now into the horizontal plane. Okay, the sensing the antenna is now in the horizontal plane. The antenna on the test at 15 degrees tilt, and we are recording we'll call that minus 5 dB. We're now going to tilt the antenna on the test another 5 degrees to 20 degrees angle. Okay, with the sensing antenna in the horizontal plane, the antenna under test at 20 degrees, we are recording minus call it 4.1 dB. Now I'm going to move the sensing antenna into the vertical plane. Okay, the sensing antenna is now in the vertical plane at 20 degrees tilt of the skew planar plane. We are recording minus minus 4.2 dB. Now tilt another 5 degrees. Okay, with the sensing antenna still in the vertical position, and we've now got the skew planar plane tilted at 25 degrees, we are recording minus 4.2, minus 4.2 dB. Now I'm going to move the sensing antenna into the horizontal plane. Okay, with the antenna on the test at an angle of 25 degrees, sensing antenna in the horizontal plane, we are recording minus 3.5 dB. Tilt another 5 degrees, so total angle of 30 degrees now. Okay, with the antenna under test now tilted at 30 degrees, the sensing antenna in the horizontal plane, we are recording minus 2.8 dB. Now shifting the sensing antenna into the vertical plane. Okay, antenna on the test at 30 degrees. The sensing antenna in the vertical plane, we are recording minus 3.8 dB. And shift another 5 degrees angle to total of 35 degrees. Okay, with the sensing antenna in the vertical plane, the antenna on the test at an angle of 35 degrees, we are recording minus 3.2, minus 3.2 dB. We're going to shift the sensing antenna into the horizontal plane. Okay, with the sensing antenna now in the horizontal plane, we are recording minus 2.7 dB. Now I'm going to tilt the antenna on the test to an angle of 45 degrees. Okay, with the antenna under test now tilted at 45 degrees, the sensing antenna in the horizontal plane, we are recording minus 1.4 dB. Now shift the sensing antenna into the vertical plane. Okay, with the skew planar plane now tilted at 45 degrees towards the sensing antenna and the sensing antenna in the vertical plane, we are recording minus 2 dB. We will now shift to 55 degrees tilt. Okay, with the antenna now tilted at 55 degrees and the sensing antenna in the vertical plane, we are recording minus 1 0.8 dB. Now move the sensing antenna into the horizontal plane. Okay, waiting for things to settle down at 55 degrees tilt. In the horizontal plane, we are recording minus 2 dB. And I'll tilt the antenna on the test now to 60 degrees. Okay, now with the skew planar plane and with the antenna on the test now tilted at 60 degrees, sensing antenna in the horizontal plane, we are recording minus 2.1 dB. Now shift the sensing antenna into the vertical plane. Okay, at 60 degrees with the sensing antenna in the vertical plane, we are now recording minus 1 dB. Okay, we're going to tilt now to 70 degrees, another 10 degrees. Okay, with the sensing antenna in the vertical polarization and the antenna under test now tilted at 70 degrees, we're recording minus 1 dB. Now shifting the sensing antenna into the horizontal plane. Okay, with the sensing antenna in the horizontal plane, the antenna under test at 70 degrees, we are recording when things settle down. Minus 3.5 dB. Okay, we're now going to tilt the antenna under test to 80 degrees. Okay, with the sensing antenna in the horizontal position, the antenna under test now at 80 degrees, we are recording minus 5.2 dB. Now shift the sensing antenna into the vertical plane. Okay, with the antenna under test now at 80 degrees tilt angle, the sensing antenna in the vertical plane, we are recording minus 2 dB. Okay, we now tilt it 90 degrees, so it will be now pointed into the center of the skew planar plane. The antenna under test is in the 90 degrees position now, so the sensing antenna is pointing straight into the top of it, as if the antenna was pointing up into the sky. That is where we're looking at. So it tilted at 90 degrees. The sensing antenna is in the horizontal plane, and we are recording minus, moving all over the place, we'll call it a minus 18.5 dB, so the horizontal plane. Now tilt the sensing antenna into the vertical plane. So, interesting. In the vertical plane, at 90 degrees tilt, we are recording minus 3.6 dB. Okay, so interesting. The vertical polarization, for whatever reason, seems to be slightly favoured. In the 90 degrees plane, it is quite dramatically favoured. Interestingly, when you look at the results from the model, it's fairly consistent. At the 90 degrees tilt, we were expecting minus 20 dB, so in the horizontal we're getting minus 18.5, which is very close. In the vertical, minus 3.6 is quite different. But in all the other angles, whether the sensing antenna is in horizontal or vertical plane, is within a couple of dB, which is excellent. This is what we want, the antenna to be blind to polarization. Now the one fairly obvious thing is that these are all minus figures. When we did the test, or the reference is against a dipole, so a dipole and a dipole in the same polarization was benchmarked at 0, so everything on the skew planar plane is a negative figure irrespective of the angle of the antenna and the polarization, with the exception of the 90 degrees. They're all minus figures, and that's because there's no free lunches. We've sacrificed a bit of gain, about 3 to 5, 6 dB of gain, to have an omnidirectional antenna that is blind to the polarization of the arriving signal, which is what we want. This is what this antenna is meant to do. But we have sacrificed a small amount of gain. So that's the results. Kind of what was expected. It's somewhat consistent with the model, which is always good. And I hope you found that interesting. So once again, thank you for watching.